going into the last topic of Chapter 3 that we'll be covering, Section 6, Systems of Linear Equations in Two Variables. Here are the objectives, and we'll be giving you these as we go through the course. Now, as background, we have dealt so far with equations that actually, when we graph them, form lines. So suppose this is one line, and I'll change colors here. And then another equation is plotted on the same graph, and this is the line. Now we see the black line has positive slope. The blue line has negative slope. But there's an interesting thing that occurs at this particular point. The ordered pair, the x and the y of this point, happens to be a solution for the black line and the blue line. Even though one's negative, one's positive, they're intersecting that ordered pair, and it looks like it would be about a -1 and a 1. Now, another scenario as we move on is, suppose you have one line, and then you draw another line, and from another equation, and lo and behold, it looks like this. Well, we know from our last lesson that these lines are going to be parallel, and they would never intersect. And then a third scenario is you have one line, and then interestingly, when you plot the other line, it's right on top of that line. So these are the possible scenarios we're going to be looking at as we talk about systems of linear equations. There's two sets now, and as a reference, here this type has just the one solution. Here this type has no solution. Now here, since the solution of one point on one equation is the same as on the other equations, and there's an infinite number of points along the line, for this there would be an infinite number of solutions. So again, as background to what is operating here. And we'll get back to our regular screen and then clear this up. So the first thing they're asking us to do is see if an ordered pair, 2, 1, is a solution for two equations. And you might say, well, how would I go about doing that? Well, you would substitute the x and y values into the equation and see if, in fact, they make the statements true. Okay? Now, a couple of key words we want you to add, and we see them down here below. If it has at least one solution, one intersection, we say the equations are consistent. That would be that first scenario where there's one intersection, or the last scenario where there's an infinite number of intersections. If the lines are parallel and there is no solution, and again, write this word down, we say it is inconsistent. There are no points of contact between the two. Now, if the equations are the same, as we see in that third scenario where the lines were right on top of each other, we say the equations are dependent, and if the equations are different and the lines are, one's negative, one's positive, we say the equations are independent. Okay, some words that you're going to be using as you put answers into your practice and later the certify. And here is a summary of what we've just said. So take any notes you want, pause as needed. And if I had waited, I see they are going through all that I gave you as background again. This is just the formal presentation of it. All right, that was our background. Let's go on to example 1, solving systems by graphing. And here this would be consistent because the lines would intersect. Now I'm assuming that you're able to graph this. I would suggest on that first one, you make a little t-chart, your X and Y intercept t-chart as a review, a 0 there, a 0 there. And if X is 0, Y is 6. And if Y is 0, X is 6. And then these are the intercepts. And we see it there on the blue line and there. It's cut off a little bit, but you can see it. And then plotting this next one, we'll use the technique of our y-intercept is 4, which is going to be right there. And then the slope of this is 1 over 1, positive. So over 1, up 1 brings you to this point of intersection. And then you read the value. It's going to be a 1 and then a 5. So again, this may run a little long. We're going to move right along. Now, for example 2, we're going to see a set of equations that they're stating requires estimation. We're going to have to guesstimate here a little bit. So let's raise it up. These are our equations. And again, I think probably graphing them would be a sort of a challenge. Now, often when they ask you to graph something like this using our software, they will ask you to solve for the letter y. And here it would be a negative 3y equals a negative x plus 4. Divide everything by a negative 3. Keeping in mind there's a 1 there. So this then becomes a positive y equals a positive 1/3 x. And then this is a negative 1 and 1/3. That again, a negative 1 and 1/3, our y intersect would be there. And then it would be over 3, 1, 2, 3, up 1. But usually by putting this into your software, that line would form. And then the other one is a little easier to solve. Y equals a negative 2x plus 3. So you'd have your y-intercept and then a negative 1 over to the left and then up 1. And that second line would get there. Now, as you look at this, and I'll raise it up a little bit so we can put it right in the middle here, and I'll take these other points off. We're going to guesstimate that. Well, you might guess that the x value is a 2, and the y value a negative 1/2. Well, I wouldn't pick a negative 1/2, and I wouldn't do a 2. Now, if you put these values into the original equations, they wouldn't solve it. So graphing has its limitations. So there are algebraic ways to solve these equations, and that's what we'll be moving into. Now, the actual solutions is this ordered pair down here. That would be almost impossible to pick out from a graph. So they're suggesting we're going to do it algebraically, and we will show you that shortly. Now, one method is to solve by substitution, and we will show you this here in our next slide. They give you the protocol for doing it, and we'll be doing some of this as classwork as well. Now, in example 3, we're asked to use substitution, again using algebra, to solve this. And I'm going to show you 2 ways to do it, and you can have your pick. And I'll use the whiteboard to help give me some room. Now, the way the textbook is suggesting is you look at these equations and solve for what are the letters. Well, one of the ones that we're famous with is this y here. Solve this second equation for y by bringing over the 2x as a negative 2x to this side, and then plus 3. Now, I now have a value for y that I will highlight here in red. This is what y is. I'm going to take this value for y and substitute it in the other equation. So now it looks like this. X minus 3. There's what I've written so far. Now I'm going to put my value for y in there. Negative 2x plus 3. And then this equals 4. Now I solve an equation with only one letter as a variable. So this is x. Now, negative 3 times negative 2x is a positive 6x. Negative 3 times a positive 3 is a negative 9. And then this equals 4. So I'm getting rid of the parentheses. Again, using techniques from earlier lessons. Combine like terms, I get 7x. I'm going to transpose this to this side. And on this side, it becomes a positive 9. So this gives me 13. So I have then x, when I divide both sides by 7, x is 13/7. Okay. Now, I have a value for x. I need a value for y. Well, in this equation here, I have y equals a negative 2, but I have that x now is 13/7 plus 3. Well, again, it's going to be easier if I get rid of that fraction. So I'm going to multiply everything by 7, and then I'll get my value here. So this becomes then 7y. Here the 7's cancel out, and I get a negative 26. And I get a plus 7 times 3 is 21. Okay, I'm going to combine like terms here, and I get here a negative 5. 7y equals negative 5. Divide both sides by 7. and I get y now equals a negative 5/7. So my ordered pair is 13/7 and a negative 5/7 using algebra, because I wasn't able to pick these out of the graph. This is very, very difficult. All right, let's go back to our regular screen and see what they have. I'll leave my work there for a moment, but they've worked it through, and you see they get the same answers, 13/7 and a negative 5/7. This was the algebraic way of working it out through substitution. Now, I said I'd show you another way of doing this. And going back to our whiteboard, now what I've done here is I've solved each equation for y. So this equation I solved for y. This other equation I've solved for y. Now, another method of substitution is I can let my y's equal each other, because we know that y equals y, and this y is this, which is 1/3 x minus 4/3 equals a negative 2x plus 3. Now here again, you only have x as the single variable, and to solve it, you'd have to go through getting rid of the decimals. This would give you an x value. And then you could put that x value again like we did. So a little modification. Now this example was quite tedious, and I'm assuming that we're not going to have any that are quite so difficult. All right, let's go back. Now in example 4, we'd like you to write these down. And they're asking us to solve it by substitution. So I'll work this one out for you too on the whiteboard. So we have this equation in standard form. This one's in standard form, but if I solve for y, again, bringing over my negative 2x, or the 2x becomes a negative 2x minus 3. Now this is our value for y that we're now going to take and substitute here. And I'll write it over here. So 6x plus 3. And now I'm going to put the value for y that I found, a negative 2x minus 3. And then this equals 14. So I go 6x minus 6x minus 9 equals 14. But notice an interesting thing happens here. 6x minus 6x is 0, and I end up with an equation 9 equals 14. That's not true. So whenever you get a situation like this, where you've eliminated something and you have an untrue statement, it indicates that these original equations were actually parallel equations, and there's no solution. They are inconsistent. And let's take a look at what they said as we go through this. And we'll clear that up. So you're getting a false statement. Indicates the systems are inconsistent. They are parallel lines, therefore no solution. Now, there is another method of solving algebraically equations, not by substitution, not by graphing, but in this case it's described as by addition. So some background information, and I will go through the process, and it's sometimes also referred to as the method of elimination, where you are eliminating one of the variables through the process of addition. And I'll illustrate that for you on the next slide. This will be example 5, and we're looking at the addition method. I'll switch to whiteboard shortly. So I've copied down the 2 examples. Now, the substitution method wouldn't work here because we don't have any letter by itself. If we solve for a letter, we'd get fractions. So this is the protocol I'd like you to include in your notes. You're going to write these over on the left side of your page. Then you're going to put like an arrow here, because we're going to modify these equations into equivalent equations where one of the letters will add out. So we're going to put a bracket here, and then a bracket there. And remember, we are allowed to multiply everything by something. Now, again, these take a little bit of study, and there's a little bit of art. So if this were a number, and this subtracted that same number, these would cancel out. So what could we multiply this equation by, every term, all 3, and this one, all 3, so that these would cancel out? And the answer is, if we multiplied this one by 7, and if we multiplied this one by 3, this would become a 21x that I'll put here. 5 times 7 is a positive 35y, and 7 times a negative 3 is a negative 21. Okay, we've modified every term. Now here, this is going to be a negative 21, which is what I'm looking for, something that will cancel out. Now 3 times this is 6y, and then this times this is a positive 21. Okay, so now we draw our line and add this up. Here, this is a 0. This is going to be 41, and this is a 0. So we get, well, the y, I'm going to put the y there. So divide both sides by 41, and we get y equals 0. Okay, now we can go to one of these original equations, and here, if we copy this first one, 3x plus 5 times 0 is 0 equals a negative 3. We're going to get x equals, dividing both sides by 3, a negative 1. So our ordered pair then is a negative 1, comma, 0. And the method I used to arrive at that was the addition or the elimination method, where we set the equations up in standard form, modify them so that one of the letters will cancel out, and then solve for the other letter. And then once we find a value for the other letter, introduce that in one of the original equations and solve for the other letter. Okay, let's check this out. Going back to our regular work here. In example 6 now, we're taking a look at this and seeing that here, this will be a system of infinite solutions. Now, what does that look like? Well, I'm going to, again, use the whiteboard, or we can actually, just to save a little bit of time, use what they have described here. There are 2 equations. We can write them down. And as we modify them, an interesting thing happens. and you can see it right here, that everything cancels out and we end up with 0 equals 0. So looking at these equations, these are actually the same equation disguised in algebra. Because when we got to them, notice we have a negative 6x plus y equals a negative 12. If I multiply this one by a negative, I get the same thing. But having the opposite signs, everything cancels out. Now, does 0 equal 0? Is that a true statement? Yes. So when it's a true statement like this indicates the lines were actually the same. And there's an infinite number of solutions. They are consistent because you have at least one. And the equations, since they are the same, are considered dependent. Now, there are 3 more examples to do, and we're running at 26. So I've decided that I'm going to make this presentation in 2 parts, so you have sort of a break. So this was the mechanical, graphing, substitution, and the addition methods. Now, in our next presentation, we'll do applications where this kind of problem in 2 variables are solved. Now, they are quite challenging, and again, we'll treat it as a separate thing, and we'll wind up part 1.